Welcome back. We are to the third and final part of confidence intervals, and we are now going to find confidence intervals using the standard deviation. That is for sigma. And when constructing a confidence interval estimate of a population standard deviation, that's sigma, we construct a confidence interval using this is going to be new for us, a chi-squared. So distribution. And it has degrees of freedom, again, of n-1. And we'll note that as n gets larger and larger and larger, meaning the degrees of freedom gets larger and larger and larger, it becomes more and more bell-shaped. And we'll talk more about that with the properties here. And so our typical chi-squared, it starts at 0, which is different than the t or the z, which go off to negative and positive infinity. So it starts at 0, and it's often skewed right. So it's more often than not, it's got this big, long right tail, bunched up like that. Some properties of chi-squared distribution. The chi-squared distribution is not symmetric. We can see it. So this one here's more typical of the way they look. The values of chi-squared can be 0 or positive. So chi-squared can't be negative, unlike t and z, where they could be negative. The chi-squared distribution is different for each number of degrees of freedom, right? It's dependent on n. And we can even see the 3 different graphs here. As the number of degrees of freedom increases, the chi-squared distribution approaches a normal distribution. And you can kind of see that a little bit as we're there. So we're going to practice a little bit using this. We're going to be using this table here. This is called a chi-squared distribution table. This entire packet that I'm going to be using here in just a moment is available in Canvas for you. You can print it out if you want to. This is the same one that you can find the t distribution as well as a z distribution. But today we're going to be using chi-squared. So we're going to find, for example 10, we're going to find the critical region of chi-squared corresponding to a confidence level of 95% and n equals 22. So I'm going to actually write this up here. So this is the first one with 10. And I want to draw the distribution. Okay, often skewed right. Here's our chi-squared. And we are actually going to have 2. So we have here, so 95% is our confidence level. That means alpha is 0.05. And we're going to split that up to here and here. And that's going to get half of that, just the 0.025. The other half is going to go there, 0.025. And here we're going to end up with chi-squared left and chi-squared right. So we're going to end up with 2 of these. And this is where our table comes in. And by the way, n is 22, which means our degrees of freedom is 21. All right, to our table. Now, I want to point out with this chi-squared distribution table, all of these are assuming area to the right. Now, that's the opposite of what we've been doing. So this is area to the right. So let's start with our left one here. And I want to point out that in the middle here is 0.95. So in actuality, the area to the right here is 1 minus 0.025. Two ways I can do this. 1 minus 0.025, 0.975, or I could go 0.95 plus 0.025. Either way, it gets me the same value. But the area to the right in this case is the 0.975. Degrees of freedom of 11. And here we go. So the area to the right is the 0.975. That's here. Degrees of freedom is 11. that means we are here. This is going to be a 21, not 11. For our degrees of freedom, that's 10.283. 10.283. Area to the right, chi-squared r. Again, area to the right is 0.025. Degrees of freedom is still 21. 0.025 degrees of freedom is 21. And here we are. 35.479. So approximately equal. This is 35.479. Let's double check that second one real quick. 0.025, 21. Yeah. All right. So here we are. The second part of example 10. Once again, I'm going to draw a chi-squared. And in this case, my degrees of freedom is 24. And to 99%, that means alpha is 0.99. I'm sorry, is 0.01. So once again, we're going to split that. So half of 0.01 is 0.005. Have this here. We are looking for chi-squared left and chi-squared right. All right, so we'll get a handy dandy table here. Area to the right here, and again, real quick, 0.99. Area to the right here is 0.99 plus 0.005, that's 0.995. So here we go. So degrees of freedom is 24, here we are. And the area to the right is 0.995, that's this first one right here. So 9.886. And area to the right here is 0.005. Again, degrees of freedom is 24 in this case. And 0.005 is way out here. Let's see there. 24, so 45.559. And that's how you find those values. Now, what are we going to do with those values? I'm going to show you. So we're going to construct a confidence interval for the population standard deviation. That, of course, is sigma. And here's what this is going to look like. Now, this might look a little backwards to you, like the right one is actually on the left, and there's a reason for that, but these are the way that we're going to find this out. And here we go. So we have 22 full IQ scores. This is example 11. 22 full IQ scores have a standard deviation of 14.3. So here is my S. Consider the sample to be a simple random sample and construct a, oh, I didn't mention this here. The sample has to be simple random sample and the population must be normally distributed. If it's not normally distributed, then we can't do this. All right, consider the sample to be simple random sample and construct a 95% confidence interval for an estimate of sigma. All right, 95, that means that alpha is 0.05. Alpha over 2 is 0.025. N is 22, which means our degrees of freedom is 21. Now, I want to point out that we've already done this very nicely. That's this one here. Right, sample size of 22, same alpha and everything. So we actually have, from up here, we actually have chi-squared left and chi-squared right. So chi-squared left is 10.283. Chi-squared right is 35.479. We also have S. Standard deviation of 14.3. So we have everything that we need. So this is the square root of 21, right? 1 less, n minus 1, times 14.3 squared over chi-squared right, that's here, 35.479. And here we have 21 times 14.3 squared over chi-squared left, which is 10.283. Our calculators ready? All right, so square root of 21 times 14.3 squared divided by 35.479. There it is. And once again, square root of 21 times 14.33 squared divided by 10.283. Again, your calculator may work differently than mine. You may need to add parentheses or something like that. And that gives us here 20.4355. And there is our confidence interval for our sigma. This one, there's no magical thing in the calculator that we can do. We actually have to do it by hand, unfortunately.